Hello students, in the previous session we learnt how to find derivatives using first principle. Now let us look into the solutions of the assignment problems. Problem number 1, find the derivative of x cube minus 27 using first principle. Let f of x be equal to x cube minus 27. We have f dash x is equal to limit f of x plus h minus f of x upon h as h tends to 0. That implies f dash x is equal to limit x plus h whole cube minus 27 minus x cube minus 27 upon h as h tends to 0. That can be written as limit x plus h whole cube minus x cube upon h as h tends to 0. That is equal to limit x cube plus h cube plus 3xh into x plus h minus x cube upon h as h tends to 0. Here we have expanded the binomial a plus b whole cube is equal to a cube plus b cube plus 3ab into a plus b. That is equal to limit h cube plus 3xh into x plus h upon h as h tends to 0. That is equal to limit h into h square plus 3x into x plus h upon h as h tends to 0. Therefore, f dash x is equal to 0 plus 3x into x plus 0, that is equal to 3x square. Now, problem number 2, find the derivative of the function f of x using first principle. F x is equal to x minus 1 into x minus 2, that can be written as x square minus 2x minus x plus 2. That implies f of x is equal to x square minus 3x plus 2. Therefore, f dash x is equal to limit f of x plus h minus f of x upon h as h tends to 0, can be written as limit x plus h whole square minus 3 into x plus h plus 2 minus x square minus 3x plus 2 upon h as h tends to 0. That can be written as limit x square plus h square plus 2xh minus 3x minus 3h plus 2 minus x square plus 3x minus 2 upon h. After cancelling out the terms, we are left with limit h square plus 2xh minus 3h upon h as h tends to 0, that is equal to limit h into h plus 2x minus 3 upon h. On cancelling h as common factor, we are left with f dash x is equal to limit h plus 2x minus 3 as h tends to 0. That is equal to 0 plus 2x minus 3, and therefore, the answer is 2x minus 3. Now, let us look into the algebra of derivative of functions. Since the very definition of derivatives involves limits in a rather direct fashion, we expect the rules for derivatives to follow closely that of limits. We can collect these in the following theorem. First theorem, let f and g be two functions such that their derivatives are defined in a common domain. Then we have derivative of sum of two functions is sum of the derivatives of the functions, that is dy dx of f of x plus g of x is equal to dy dx of f of x plus dy dx of g of x. Next, derivative of difference of two functions is difference of their derivatives of the functions, that is dy dx of f of x minus g of x is equal to dy dx of f of x minus dy dx of g of x. Similarly, derivative of product of two functions is given by the following product rule: d by dx of f of x into g of x is equal to d by dx of f of x into g of x plus f of x into d by dx of g of x. Similarly, we have fourth one here. Derivative of quotient of two functions is given by the following quotient rule: wherever the denominator is not 0, d by dx of f of x upon g of x is equal to d by dx of f of x into g of x plus f of x into d by dx of g of x divided by g of x whole square. As in the case of limits, this theorem tells us how to compute derivatives of special types of functions. The last two statements in the theorem may be restated in the following manner, which aids in recalling them easily. Let u be equal to f of x and v be equal to g of x. Then u v dash is equal to u dash v plus u v dash. This is referred to a Leibniz rule for differentiating product of functions, or the product rule. Similarly, the quotient rule is u upon v dash is equal to u dash v minus u v dash upon v square. Another theorem here: derivative of f of x is equal to x raised to n is n x raised to n minus 1 for any positive integer n. Look at the proof. By the definition of the derivative function, we have f dash x is equal to limit f of x plus h minus f of x upon h as h tends to 0 is equal to limit x plus h whole raised to n minus x raised to n upon h as h tends to 0. The binomial theorem tells us that x plus h whole raised to n is equal to nc0 into x raised to n plus nc1 into x raised to n minus 1 into h plus ncn into h raised to n, and hence x plus h whole raised to n minus x raised to n is equal to h into nx raised to n minus 1 plus so on plus h raised to n minus 1. Thus, d by dx of f of x is equal to limit x plus h whole raised to n minus x raised to n upon h as h tends to 0 is equal to limit h into nx raised to n minus 1 plus so on plus h raised to n minus 1 upon h as h tends to 0 can be written as limit nx raised to n minus 1 plus so on plus h raised to n minus 1 as h tends to 0. So, we have it as nx raised to n minus 1. Now, let us discuss about the derivatives of polynomial and trigonometric functions. Look into the theorem. Let f of x be equal to a n x raised to n plus a n minus 1 x raised to n minus 1 plus so on plus a 1 x plus a 0 be a polynomial function where a i's are all real numbers and a n is not equal to 0. Then the derivative function is given by d by dx of f of x is equal to n into a n x raised to n minus 1 plus n minus 1 into a n minus 1 x raised to n minus 2 plus so on plus 2 into a 2 x plus a 1. Now, let us solve some examples to understand this. Compute the derivative of f of x is equal to 1 plus x square plus x cube plus so on plus x raised to 50 at x is equal to 1. For the solution, a direct application of the theorem tells that the derivative of the function is 1 plus 2x plus 3x square plus so on plus 50 into x to the power 49. At x is equal to 1, the value of this function equals 1 plus 2 into 1 plus 3 into 1 square plus so on plus 50 into 1 to the power 49, that is equal to 1 plus 2 plus 3 plus so on plus 50, that is obviously 50 into 51 upon 2, which gives us 1275 as the answer. Let us look into one more example here. Find the derivative of f of x is equal to x plus 1 upon x. For the solution, clearly this function is defined everywhere except at x is equal to 0. We use the quotient rule with u is equal to x plus 1 and v is equal to x. Hence, u dash is equal to 1 and v dash is equal to 1. Therefore, d by dx of f of x is equal to d by dx of x plus 1 upon x, that is equal to d by dx of u upon v, that can be written as u dash v minus u v dash upon v square, that gives 1 into x minus x plus 1 into 1 upon x square, which gives us minus 1 upon x square. Another example here, compute the derivative of sin x. For the solution, let f of x be sin x, then d by dx of f of x is equal to limit f of x plus h minus f of x upon h as h tends to 0 can be simplified as limit sin x plus h minus sin x upon h as h tends to 0. Here we use the formula of sin a minus sin b, and this can be simplified as limit 2 cos 2x plus h upon 2 into sin h upon 2 upon h as h tends to 0, which can be simplified as limit cos of x plus h upon 2 into limit sin h upon 2 upon h upon 2 as h tends to 0. Here this is equal to cos x into 1, which is obviously equal to cos x. Remember, if the function is in the classification form, we have to check the existence of limit. For this, we will find right hand limit and left hand limit at particular value of x. Let us solve an example to understand this. Find limit f of x as x tends to 0 and limit f of x as x tends to 1, where f of x is equal to 2x plus 3 whenever x is less than or equal to 0 and 3 into x plus 1 wherever x is greater than 0. Look into the solution. We have f of x is equal to 2x plus 3 wherever x is less than or equal to 0 and 3 into x plus 1 wherever x is greater than 0. At x is equal to 0, look into the right hand limit. We have limit f of x as x tends to 0 positive is equal to limit f of 0 plus h as h tends to 0, that is equal to limit 3 into 0 plus h plus 1 as h tends to 0, which can be simplified as 3 into 0 plus 0 plus 1, that is equal to 3 into 1, that is equal to 3. Now look at the left hand limit, that is equal to limit as x tends to 0 negative f of x is equal to limit f of 0 minus h as h tends to 0, that is equal to limit 2 into 0 minus h plus 3 as h tends to 0, that is equal to 2 into 0 minus 0 plus 3, that is equal to 3. This implies left hand limit is equal to right hand limit, that is equal to f of 0. Here at x is equal to 0, the limit exists. Now at x is equal to 1, right hand limit is equal to limit f of x as x tends to 1 positive is equal to limit of f of 1 plus h as h tends to 0 is equal to limit of 3 into 1 plus h plus 1 as h tends to 0 is equal to 3 into 1 plus 0 plus 1, that is equal to 6. Now check the left hand limit, that is equal to limit x tends to 1 negative f of x is equal to limit f of 1 minus h as h tends to 0. Here we are putting x is equal to 1 minus h, that is equal to limit 3 into 1 minus h plus 1 as h tends to 0. Therefore, f of 1 is equal to 3 into 1 plus 1, that is equal to 6. Therefore, left hand limit is equal to right hand limit, and hence we can see here that the limit exists. So, students, we studied about limits and derivatives. Hope you enjoyed studying it. Thank you.